So today's topic is trust region policy optimization. It was a paper that was presented in ICML 2015 by John Schumann and other people. So before we start discussing what is trust region policy updates, let's just look into the hierarchy of reinforcement learning algorithms. So the division of these algorithms is action value functions, and there is a policy gradient. So we have already worked on the action values, which is Q learning and stuff. And we have also seen in the lectures about actor critic and a little bit about A to C also. So the policy gradient, the TRPO is kind of classified into policy gradients, but it's not really the method on its own. It's an optimization technique that could be also used within actor critic. This is basically when you get the gradient, you can change it according to the trust regions, which I'll discuss. So this is the basically all the policy gradient algorithm follows similar sort of routines. So you start with collecting n trajectories for a given policy, that is an initial policy, and then you estimate the advantage function A, right? Even for the actor critic, all you are doing is you are getting the better estimate of A. Otherwise, it follows the same procedure. Then you compute the policy gradient, and then you update the policy. So let's look at what is the problem with the vanilla policy gradient, or the policy gradient without using TRPO. So first problem is that if your policy is parameterized, if it's a function approximation, then your input to that function approximation is non-stationary. At end of the step, you basically change the distribution of input as well as the output. Your output is reward or your advantage in this case. So this makes everything unstable. So one of the problem is non-stationary input data. This happens because you update your policy right here, and then you collect according to your updated policy. So another disadvantage is that your advantage function is very random when you start when you start from the very initial policies. So it's saying that you are bad to the policy, and then policy is in this loop of not detecting where the optimal path is. What we need is that we need more carefully crafted policy update. We want that when we update the policy, we want improvement, not the degradation. So the idea of the TRPO is that we can update the old policy, which is in this case the theta, to the new policy pi tilde, such that they are in trusted region apart. Such conservative policy update allows improvement instead of degradation. And I'll tell you what the trusted region or trusted distance is in this case. Oh yeah, I want to mention that first of all that we can change this particular update into the optimization problem instead. So instead of just following where the highest advantage is, we can make this particular update procedure, the theta is equal to theta old plus the alpha g. We can solve some sort of optimization that will allow the better update. So I'll show you why this is important. So RL2 optimization. Most of the machine learning algorithms is optimization, right? If you have a supervised learning algorithm, it's trying to reduce the training loss, which in turn correspond to the testing loss, or it may or may not, but we assume that it does. So what happens in the policy gradient optimizing? What is policy gradient optimizing? It's simply favoring the tuples S, state, and action such that they give more advantage, but they're not really optimizing anything, the vanilla policy gradient. So the TRPO suggests that, TRPO by the way is trust region policy optimization. It suggests that we can write down the optimization problem that allows to do small update on the policy based on the data that was sampled from that policy, so that we can ensure that there is always the improvement in the policy and there is no degradation. So first thing is, what do we need to optimize? So in any policy gradient, we have this eta pi, which is the cumulative collected reward. And this is what, this also turns into advantage as we have seen. So we collect the data with the pi old and optimize the objective to get a new pi tilde. So that's what we will do in TRPO. So we can express in this paper, not in this paper, actually in this 2002 paper, the Kakade and Lanford, they proved this identity, which is the basis of the TRPO algorithm. It suggests that the expected return of a new policy is expected return of an old policy, and then you sample the advantage from the newer policy. So it basically allows you to relate the old policy that we are trying to update in terms of the new policy. So the TRPO, the John and Schulman, they changed this particular equation, the one that is over here, which is proposed in 2002. They changed it to this equation. The only thing they have changed is this part, this particular part. They have changed it into the discounted visitation frequency, which is this over here. And then this stays, this is just the advantage function, and then the probability of transition from that particular action. So what do we get here is that we have the new expected return. It's based on the old expected return. And if we can somehow say that the advantage for all these states is greater than 0, then our new expected return is guaranteed to be the improvement over the old policy. And this has not been done. We generally just don't do that. We generally just update in terms of A, and then we simply flow the gradient into the old policy and expect something to happen. But this is the guaranteed improvement from the old policy in terms of the expected return of the new policy from the data that is sampled from the old policy, which is quite interesting, I think. So just want to say this equation again. This is a quite important equation. So this, the rho pi is the state visitation based on the new policy, and this is the new policy itself. However, the problem is that this, the rho pi is very difficult to estimate. So it's very difficult that we can optimize this particular function as its current form. So we cannot do that optimization right away using any optimization technique. So what TRPO suggested is that we can change this term, the state visitation of the new policy, to the old policy, because we already have the data which is sampled from the old policy. So we can change this, and instead of calling it eta pi tilde, we'll call it L pi tilde. So it's obviously changed. So there is two different functions, right? But if we can approximate what is the difference between these functions, if we can approximate the lower bound of the difference between n and L, we can have a good local approximation of n. So I'll show you what I mean. But I hope you understood that we changed the idea of changing this is to make it more simplified for optimization, because we already have the data which is sampled from the pi policy, not the pi tilde. That's a new policy that we don't even know what it is yet. So yes, what we wanted from the beginning was that we wanted to estimate the n, which is the expected return of the new policy. What we did was that this is very difficult to estimate, so we converted this into L, which is slightly simple to estimate. So we are saying that this L term is the local approximation of the expected return of the new policy. However, this is only accurate in certain region. So it's not accurate, it's not the global estimate of the n. Obviously, this is only a local estimate, and it's only encapsulated within certain region called trust region. So in that trust region, if we update our policy, there is a monotonic improvement guaranteed. So what I mean is this, in this green region, the L is corresponding to the actual eta, which is the return of the new policy. If you go in the red region, you basically diverge. There is a divergence between the L and the eta. So I mean this. This is the N, this is the eta. This is what we are trying to approximate. So in the green region, the L is very close to N, but sorry, I mean eta, and in the red region, it diverges. And this, the divergence step that we choose is the hyperparameter called delta. So what this diagram shows is that if this is my old parameter of the policy, if I update in this green region, I can guarantee that there is a improvement in this direction. So it turns out that the TRPO paper suggests that there is a direct relationship between the N and the L. And there is a proof that was given in the 2002 paper by Kakade and Lanford. This was given in 2002 paper, so they're just extending on that paper. So this is the identity that is already there, that already exists, and it says that the expected return, the actual expected return, is greater than the local expected return minus this particular, the KL divergence, maximum of the KL divergence between the new policy and the old policy, where C is this particular value. So there is always a monotonically improving, we can always improve the policy if we can sample the policy using this particular function. If we can just take the argmax of a policy that satisfies this equation, that means we are in the bound of the expected return of the new policy. So this algorithm is called minorization and maximization. What I mean is if this is the actual eta function, what we do is, this is our first step of the update. We come here and then this is our surrogate function, which is going to be the L function. In this case, it's going to be this guy, the L minus CD of max. So what we're going to do is, in order to estimate the good next policy, we'll just do maximization of this particular function, because that's going to be the lower bound of this L function in the local neighborhood. So if we keep doing this, we make sure that the policy is always improved at every step. So far this was just a theoretical background without discussing what is a parameterized policy. So how does it turns out to be the parameterized policy? Because our policy is estimating function, right? Function of theta. So how does this work with the parameterized policy? So now the policies are parameterized according to the surrogate function. The surrogate function that I showed you in this one, instead of pi, it becomes theta, because now the pi is the parameter of is the function of theta. So we can simply change this to this equation. In practice, the C, when we put the C value is already given in the paper. If we use that C, these update steps are very small. So these steps, when you improve from this black dot to this black dot, is very, very small. So you have to take lots of steps in order to make any improvement. So this is not good. What they suggested, the TRPO paper suggested, is that one way to take the largest step is to constrain the KL divergence between the new policy and the old policy, that is the trusted region. So instead of using any C, we'll simply constrain that we can maximize the L. At the same time, we'll subject that the D of the KL divergence, maximum of the KL divergence between the older parameter and the newer parameter is less than some hyperparameter. So it's not C anymore. We can stochastically update the policy instead of changing it small step by step. So this is how you will solve this equation. That's how they solve this equation. So we have to solve this equation. And the way our problem is that we have to maximize on the thetas such that this equation is maximized. And yes, they also changed the max KL divergence to the mean KL divergence because they said that it's better to optimize the mean of something instead of a max because it's not the best way to optimize this. And they didn't really provide any. They didn't provide anything on this particular subject, like why should they use max instead of mean, and if they cause any differences. So I assume it works. So they converted this max into mean. And what they did was they did the linear approximation of the L, and they did the quadratic approximation of the KL. So this could also be seen from that graph that I showed. The surrogate function is quadratic in nature, whereas the L itself is the linear in nature. So they did this approximation, and they said that L could be converted into G dot this particular thing, and then the KL divergence, mean of the KL divergence could be converted into the quadratic form like this, where G is the differentiation of L, and then this is the Hessian matrix. So in order to solve this KL-penalized problem, they make the linear approximation of L in the quadratic of the KL term, and the solution of this equation becomes this. If you want the new parameters, you simply find this, which is F is a Hessian of this particular equation. So F is just the second derivative of the KL term. But it's very computationally expensive to calculate this particular Hessian matrix. So they said, okay, we're going to approximate this Hessian matrix in order to make this algorithm more computationally inexpensive. And they use this technique that already exists from maybe 40, 50 years called Conjugate Gradient algorithm. So what Conjugate Gradient does is that it can calculate F inverse of G, which is F is the Hessian matrix here. It can calculate this without even knowing what F is. So I'll just give you a very quick intuition behind it. The paper does not give it, but I'll give you that. So Conjugate Gradient algorithm approximates the X is equal to A inverse B without explicitly forming any matrix A, where the A comes from this quadratic equation. And the way it works is that if you have this convex surface, in the actual gradient descent, you will move in the purple direction. So you can see that if you can see the purple line, you can see that it's making multiple steps. But when it's a conjugate gradient, the next direction that you will take is not the direction of the grad. Instead, you will take a conjugate of the green line. And conjugate is not a right angle, it's not orthogonal, but it's orthogonal according to the surface. So if surface is stretched out, the conjugates will be stretched out too. If it's a pure surface, then it's always going to be 90 degrees. So this makes sure that the gradient does not flow into what we have already flown through. So this is what they used in order to find the Hessian matrix. So what is TRPO? TRPO is that what we discussed so far was that we simply have to maximize this particular term in terms of theta. But what TRPO is that they put the hard constraint on this particular equation. They said that we have to maximize L theta with respect of theta, and then we subject this KL divergence term is less than or equal to delta. The solution remains almost same. First, this delta is a hyperparameter that remains fixed over the whole learning process. To solve this particular equation, you can again just convert it into, you can use the Lagrangian, which turns out to be this form. And then you can differentiate it with respect to the theta, and then you eventually get this solution, which is almost same if the F here is again Hessian, which we can compute using the conjugate gradients. And then you get this term, which is half of the step that you take with respect of F is equal to delta. This particular condition that you see is coming because of this constraint that we put on the equation. So what it turns out is that you can calculate the steps and you can rescale them back in order to satisfy this particular constraint. So your step size that you will take in your gradients will eventually be of this form. So you have S, which is unscaled, and then you will put this particular scalar value, you will multiply this by this particular value, and then this ensures that this constraint is followed. So the TRPO algorithm looks like this. You collect, it's almost same as the policy gradient, you collect n trajectories and then you estimate the advantage function. You could also use actor critic here if you want a better advantage function, better estimate of advantage function. You compute the policy gradient G, and then you compute, this should be F here, or H is fine too. You compute the H inverse G using the conjugate gradient, which minimizes this. These two lines are minimizing this particular loss. And then eventually you scale the step size, and then you add that to your gradient. You multiply that to gradient. And this ensures that your update is happening in the trusted region. So that's the TRPO algorithm. And I just want to show you the results that they got. It's not very clear what is the advantage of in terms of results, but these are their TRPO results. And they're using, I've not really told you about what is single path and Vine. This is just a sampling techniques. And I think that Rufan, who's the next presenter, he'll discuss this because it's very similar. The papers are very similar. So he'll most likely discuss this techniques. I kept what is the TRPO and what is the trusted region and how we can optimize it. So this is the result that they get. So it's not very clear like why are they improving. It seems like they're improving, but that's it.